Hi everyone, I'm Weihai Shen, a PhD candidate from Stony Brook University. Today I'm going to present our work, Mako, speculative distributed transactions with geo-replication. This is a joint work with our collaborators from Google, Microsoft Research, and UPenn. Our work targets transactional systems. A transaction wraps multiple read-write operations into one large operation. For concurrent transactions that are guaranteed to execute it atomically in serializable without interfering with each other. Transaction makes concurrent programming much easier, so it's widely used by many large companies to build their online services and applications. In general, there are two types of transactional systems. The most common and widely used ones are distributed transactional systems, such as Google Spanner or TiDB. They usually share data across many independent servers to have near-ideal scalability. And then the data is replicated to the distant data center to have fault tolerance. On the other hand, there is another type of transactional systems, single-server, multi-core transactional systems. They're incredibly fast. They usually can process a few million transactions per second per node, because they don't have because the network overhead will significantly slow down the system performance. But they usually can scale out to multiple nodes. They also don't have replicas, both of which add network overhead. Here, there is a huge gap between two transactional systems. We want to ask the question, can we have a system that achieves the best of both worlds? Super high per node throughput, high scalability, and fault tolerance. To answer this question, an existing solution uses ultra-fast network, such as RDMA, to make a distributed system well connected as if it was a single big machine. And in fact, many prior systems have adopted this approach, such as FARM, DocTM, or others. But RDMA doesn't work in geo-replicated setups. That's the problem. Geo-replication is very important for many online services and applications to tolerate data center failure. We also want that. So next, let's see a classic design with the geo-replication support. Take Spanner, for example. Spanner uses two-phase commit, TPC, to coordinate transaction execution across multiple shards. To have fault tolerance, it uses Paxos to synchronously replicate each TPC's step into distant data center. After replication, the next transaction can begin. We also observe that for TPC, they usually access one or several shards that are likely co-located within the same data center. So we can accelerate them with faster network. But for the replication traffic, it's often access the distant data center, and that's the really bottleneck of the system. So our idea is pretty simple. Decouple this replication from execution. Basically, just do the replication in the background, and then we run TPC without the replication to the end. The next transaction can observe its results immediately and execute. This plan sounds great. It can give us very high throughput, and if it's a cloud database, it can also lower the cost for each request. But what's the catch? First, it's at modest extra latency. I will talk later. But to be clear, our goal is not to reduce the latency for a single transaction. Second, some prior systems can also decouple replication. But they share a similar issue that they have to roll back too many unnecessary transactions during failed recoveries. Our technical contribution here is to address this issue. To understand why decoupling replication could cause this issue, let's take a step back and see the fundamental problem of 2PC, that 2PC isn't fault-tolerant. Here, we show an example of bank transaction. Alice transfers $100 to Bob. Because of the scalability reason, the balance of Alice and Bob are stored on two different servers. The coordinator broadcasts a prepare message to both shards. If both vote yes, the coordinator can commit this transaction. Otherwise, aborts. Now, imagine shard B votes yes after prepare messages, but both coordinator and shard A crash. Now, no one can recover these 2PC results. Shard B can commit or abort. Shard B can commit because shard A might have voted no. Shard B can't abort either because shard B might have voted yes, and the older coordinator might have committed this transaction on the shard A. To solve this problem, our idea is to roll back the failed 2PC results instead of recovering it. Still the same example. We first execute 2PC without replication and buffer its results. At that point, we delay the reply to the client. In the background, we use the paxes to replicate those 2PC results and track the current consistent state of the system. As more 2PC results are replicated, the consistent state advances over time. If failure happens to occur before 2PC finishes and replicates, we roll back the entire transaction and restore the system to the latest consistent state as if none of those results ever existed. But doing this have another challenge. What about other transactions that depend on this transaction? For example, we still have Alice with $100 in her balance account and transfer them to the Bob. Then Bob withdraws his newly received $100 T2. Now T2 depends on T1. If shard A crashes, the Alice transfer is lost. So we need to roll back T1. Now, for T2, it observed a ghost $100 that never existed. So we have to roll back T2 as well. To roll back those dependent transactions correctly, we group transactions into batches or epochs. Epoch boundary here is a consistent state of the system. All transactions within the same epoch can commit or roll back collectively. If the system advances to the new epoch, all transactions in the previous epochs are replicated, including their dependencies. If there is shard failure, we roll back all transactions collectively in the current epoch. This epoch-based rollbacks is efficient, but it might involve hundreds of thousands of transactions executed in current epoch, and most of which are unrelated to the failed shard. So we have to roll back too many unnecessary transactions. It's even worse for distributed transactional systems. As you might have many shards, a single shard failure becomes very common. We don't want such a single shard failure prevents other healthy shards executing some unrelated transactions. Next, let's use a simple example to better understand this problem and how we address this problem. Still the same example, we introduce a new friend, Charlie, whose data resides on the new shard server. Charlie withdraws $100 from his balance account. This is the T3. Now, all transactions are in the current same epoch. More importantly, this transaction doesn't depend on any two previous transactions. Now, suppose shard A fails, we need to roll back T1 because the T3 is also in the same epoch. So we also have to roll back T3 as well. But it's unnecessary. So to avoid such unnecessary rollbacks, our insight is to use vector clock to track dependencies and only selectively rollback transactions that might be affected by the failed shard. Initially, all clocks are 0. For T1, it touches shards A and B, so its vector clock is simply 110. And for T2, it reads T1 with its vector clock and then updates on the shard B, so its vector clock is a 120. Please note here, the vector clocks of T2 is larger than T1's. And if the vector clocks of two transactions are incomparable, then no dependencies between them. For T3, because it's independent of both transactions and only touches the shard C, so its vector clock is simply 001. And we use watermark to track the replication progress on each shard. And this watermark is the consistent state of our system. Initially, all are 0. After T3 is replicated on shard C, the watermark expands and updated to 001. We use this watermark to roll back all transactions. Because the T1 and the T2 are not smaller than our watermark, so we have roll back both. Even this T2 is fully replicated on shard B, and our watermark can still capture such dependencies and roll back it. For T3, because it's smaller than our watermark, so we can safely commit it. By using a vector clock and watermark, we can avoid many unnecessary rollbacks, like T3. Put all those together, we have Mako. Mako has 4 stages. First, a transaction executes optimistically within shard leaders. Next, leaders run the TPC to tentatively commit or abort this transaction. During this step, the transaction gets a vector clock to track dependencies. After tentative commit, its updates are sent to paxes in batch for replication in the background. To safely reply to the client, we wait until our watermark advances beyond the transaction vector clock. When we develop Mako, we spend a lot of time to make the vector clock and watermark work seamlessly with the failure recovery. But unfortunately, we don't have time to go into details. Please refer to our paper or stop by our poster session today. Let's discuss evaluation numbers. We implemented Mako on top of 3 existing systems, Silo, Genus, and ERPC. We tested it on Azure and simulated 3 data centers with 50 millisecond injected latency. Each data center had 10 servers. Each server had 24 work threads. We used 2 different benchmarks, a complex TPC-C benchmark with its default configuration, and a micro benchmark with several read-write operations. First, we measures the scalability of Mako, and it can achieve 3.66 million transactions per second. We also compared Mako with 2 types of baselines. One is a system that combined concurrency control and replication, such as the classic 2PC Paxos approach and a few other works, such as Genus and D2BC. All of them are orders of magnitude slower than Mako because all their replication are on their execution paths. Another type is the decoupled replication and concurrency control. A representative of such systems is Kelvin. Kelvin is also much slower than Mako. One major reason is execution order is predetermined, and it's very hard to exploit all concurrency potentials during its execution. Next, let's see how Mako performs during a single-shot failure. For this experiment, we implemented an epoch-based solution that rollbacks all transactions in the same epoch and use it as our baseline. We killed a shard leader at 10 seconds. We follow industry conventions to set the heartbeat timeout to be a large number, 10 seconds as well, to avoid any false positive in failure detection. The major difference here is that Mako can still save most of throughput during this 10 seconds timeout, while Epoch rollback solution can't, because it needs rollback all transactions. Finally, we evaluated the latency of Mako and two representatives, Janice and Kelvin. We used the light workload with just one replicated shard. For Mako, we can find its median latency is 60 milliseconds, in which 50 milliseconds for one RTT replication, and 3.5 milliseconds for batching optimization, and 6.5 milliseconds for watermark advancement. To wrap up here, we've seen today how Mako decouples replication from execution paths and uses vec clock and watermarks to selectively rollback transactions. This makes Mako outperforms its geo-replicated baselines and saves most transactions even during failures. Thank you for your attention, and I'm very happy to take any questions.